from Johns Hopkins. Welcome to this month's talk from the Johns Hopkins Institute for Assured Autonomy seminar series, co-sponsored by the Computer Science Department of the Whiting School of Engineering. Each month, we will have a talk on research topics at the intersection of assurance and autonomy. This seminar will be recorded. Today's speaker is Alyssa Pierson. Professor Pierson is an assistant professor of mechanical engineering at Boston University. Her research interests include trust and cooperation in multi-agent systems, distributed robotics control, and socially compliant autonomous system design. She focuses on designing robotic systems that interact with humans and other robots in complex dynamic environments. Prior to joining BU, Professor Pierson was a research scientist with the Computer Science and Artificial Intelligence Laboratory at MIT. She received her PhD degree from Boston University in 2017, her BS in engineering from Harvey Mudd College. During her PhD, she was awarded the Clare Booth Luce Fellowship and was a Best Paper finalist at the 2016 International Conference on Robotics and Automation. Today, Dr. Pierson will talk about designing cooperative and socially aware autonomy. Welcome, Alyssa, and over to you.
All right, thank you, Ken, for the introduction. And thank you for hosting me. I'm excited to share some of our research results today. So let me just go ahead and share my slides. All right, can everyone see the slides? Good. All right, so today I'd like to talk about some of our work in designing cooperative and socially aware autonomy. And to give a little bit of background on this, what I look at and what I think is really interesting within multi-agent systems is thinking about the different applications of problems that we have, where we can think about each of these applications in increasing complexity, both in the interactions that the agents have with one another, as well as the complexity of the environment that they're working in. And so, for instance, a kind of very popular real-world example of these multi-robot or multi-agent systems is, for instance, warehouse automation. And you can think of this as a highly structured environment where the robots have a mapped indoor space, and the interactions are fairly well known because they know that they're only working with other robots. We can think about increasing complexity of the environment and think about applications in things like crop monitoring drones, where now you've moved indoors to outdoors. And so you have uncertainty, maybe from needing to map the environment, maybe needing to explore or seek out information, but the interactions remain fairly simple or fairly straightforward between the team. We can also think about increasing the complexity of interactions in the sense of looking at things like autonomous robotic herding. And here, this is actually a photo of human-driven cattle mustering in Australia, where they have helicopter pilots fly very close to the ground to move herds of cattle over long distances. And so you can think about, if we start to replace these kind of dangerous human professions with robotic systems, your interactions are going to increase a lot, because now you're dealing with these non-cooperative cattle agents, and it's not something that you can directly communicate with like in traditional robots. And finally, if we think about another common example where you have very complex environments and very complex interactions, and that's the case of autonomous driving, where you have autonomous vehicles in unstructured environments, really needing to interact with human drivers and all the creative ways that human drivers can make decisions within an environment. And so as we think about a lot of these systems, and as we think about the multi-agent design, there's kind of a traditional approach in robotics to think about it in terms of either having an all cooperative, equally performing team on one end, or on the other end, to have all of these malicious, to maybe have a team of good guys, and then one or more malicious agents that you either can identify or have very clear bad objectives. And you know, really ultimately, what I'm interested in is everything in between. So how do you look at all of those things between everything being equal and everything being cooperative to the point of being malicious? And so what does that include? Those include teams where you might have performance variations among the agents themselves. So not everyone has equal performance. Maybe there's uncertainty in the objective or the uncertainty in the level of cooperation between the different agents. Another question to ask is, what does it mean to be non-cooperative? What does it mean to have agents that aren't aligned with your goal, but also aren't malicious in their intent? And finally, how do we account for human teammates as we start designing these multi-agent systems where you know, we need to be able to interact and design our systems around humans without requiring the humans to necessarily adapt to the specific robotic framework. And the crux of this is that if we can understand these interactions among the agents in the team, this will allow us to design safer and more robust systems overall. And ways in which that we can start to understand that is we can ask a few questions. And these are kind of questions I'll continue to revisit throughout the talk, which is, how do we interact with unknown agents? So if we don't know the decisions the other agents are going to make, whether they're robots on another team or humans, how can we still safely interact with them and achieve our goals? Another question is, how do we understand the actions of others? So what does it mean to interpret these different types of interactions for robots? And finally, if we can understand the actions, how do we respond in a predictable manner, which is especially important when we're looking at human-robot teams, where we don't just need to understand the humans, but also respond and act in a way that the humans can understand as well. A lot of my work draws on inspiration from a very rich field of research. Typically, the kind of toolkit that I use approaching these problems looks at a lot of rooted fundamentals in controls and game theory. So looking at these types of, you know, continuous system techniques, designing the inter-agent interactions, as well as looking at, you know, rich resources between the different dynamic interactions and, you know, looking at the different ways in which we can model how agents interact and cooperate. So in this talk, I'm going to kind of visit three main topics as we think about this cooperative and socially aware autonomy. The first is I'll talk a little bit about interacting with unknown agents. So how do we quantify congestion in an environment if we're looking at autonomous driving? And what are ways that we can define risk metrics? So if we want to have variations in the risk that the agents can take, what does that mean? Next, I'll talk about some of our work on social behavior for autonomous vehicles. So how can we use tools from social psychology and tools from game theory to better inform the decisions that our autonomous vehicles can make? And finally, I'll share a little bit of new results on what I'm calling here socially aware robot design. So this is a kind of more recent project over the past year where we looked at designing a UVC equipped mobile disinfection robot and thinking about the kind of bigger questions behind designing this robot for humans that also includes a technology that is not necessarily safe for humans to be exposed to on a regular basis. So weighing the design decisions and the planning decisions about how can we make sure that we're only helping people and not, you know, having adverse consequences. So starting off, I'd like to talk a little bit about some of our work in quantifying congestion and risk. So as I mentioned before, the big question in navigating cluttered and congested environments is, how do we account for all the unknown agents? If we think about highway driving, how do we account for, you know, a lane splitting motorcycle, which isn't something that we necessarily see all the time, but can happen. And in city environments, if you think about how hectic and cluttered, a city street is, you might have bicyclists, you have pedestrians stepping in and out of traffic. You also have vehicles in, double parked, unloading goods and supplies. And all of these things create very complex and rich environments that we as humans know how to navigate. But as a robot, we need to think about how to design all the ways to maintain safety as we move through these environments. And so one kind of naive approach might be to say, okay, well, if we don't know everything about our system, maybe we'll just kind of create these bubbles. So if I can say, I'm not exactly sure where this car is, well, I'll make a little bubble around it and say that if I avoid that bubble, then, it's okay that I don't know exactly where the car is because, I've padded my uncertainty a little bit. And the more uncertainty you add, the larger you can create these bubbles. And at some point in highly congested environments, you create such a conservative estimate that you can no longer find feasible trajectories through that environment. So only thinking about uncertainty as just padding these bubbles in all directions can really break down when we're looking at highly cluttered and highly congested environments. So instead, what we sort of looked at is can we still have the same sort of intuition, the same minimal information representation. So we're not trying to do full behavior prediction, but instead, can we rely on a minimal set of information to quickly assess safe versus unsafe regions for navigation? And so instead of just using the position here, we said, okay, let's say we also have the velocity information. So we can not only see where the car is, but also the direction that they're moving. And we're going to make a few assumptions. We're going to say that that all the other agents are self-preserving, which is to say that we are not intentionally trying to hit cars, and these other agents and cars and pedestrians are also not actively trying to run into us. And for the near term, over this observation, we're going to assume that whatever velocity they're moving at, they're going to continue moving in that current direction. And we're going to update our estimate quite a bit. So it's not like we're assuming a really long horizon of that current trajectory, but just over a few seconds, they'll continue in that direction. And so what we created is this kind of congestion cost, where we take an uncertainty estimate, a form of a Gaussian that looks at, modeling some uncertainty in the position, and then we're going to skew it by a logistic function in the direction of the velocity, which intuitively will skew that uncertainty along the direction of motion. And so in the contours on the right, we have kind of this contours of this congestion cost function over the cars. And you can see that if a car has a really high forward velocity, it will end up creating these kind of skewed bubble regions really far out in front of the car, versus if we are confident that it's not moving in another direction, it's not going to increase our uncertainty in that range. And then we define what we're calling a risk level set, is that for our ego agent, our planning agent, we can choose some allowable cost threshold, and we're only going to plan our actions within that cost threshold. So we're going to say every location in the environment that is above a certain cost, we're going to say is not allowable for traversal, and plan only in everything that falls below a certain threshold of cost. And so to do this, we can actually find, looking at data sets such as the NGSIM and HI-D data sets, that humans also have what appear to be low, medium, and high risk thresholds. And so what we're showing here is in the video, the red car is just one of these cars within the data set, and it comes up on this traffic jam. And as it comes up on the traffic jam, its risk increases as it's moving forward and everything's stopped up. It actually swerves out of the way and moves into kind of a lower cost region as it continues its trajectory. And what we're really looking at here is can we try and figure out, if we were to put an autonomous car on the road, can we say this is what a low risk vehicle behavior might look like versus a high risk vehicle behavior, given kind of past observations along that roadway or past observations of other human drivers. And if we were to create kind of a simple simulation of an autonomous vehicle, this is what it means to be a low risk driver. So a low risk driver will choose a very low tolerable risk threshold. And as it tries to drive, these gray regions indicate all the regions in the environment which are too risky to try and navigate to. So as it's going along the highway, it largely makes 1 or 2 lane changes. And then, it really isn't making other lane changes because, as you can see, a lot of the regions would appear gray, and its kind of lane change planner is seeing that as unavailable. And so it doesn't make the lane changes. But if we increase that risk threshold and we increase the tolerable risk for the vehicle, we notice that those gray bubbles are a lot smaller. And what we start to see is what we would call more aggressive behavior, where suddenly that higher risk threshold allows it to kind of weave in and out and start to make a lot more lane changes through this traffic. And so we think this is perhaps one way to think about having kind of a risk tolerance with minimal information that is really just a safety net that you add in your other levels of planning. So we don't think this is the only tool that you should use, but instead provides a very quick estimate of allowable planning space and allowable risk that can easily integrate with more complex, predictions and semantics. So this covers, a quick assessment of the cars on the road, and then on top of that, you might add some finer behavior predictions for the immediate vehicles that you're interacting with. But a question with that is to make this minimal safety net, we also assumed that we had position and velocity, and those assumptions require reliable object tracking. And so to take it a step further, we asked, well, what happens if we actually say that even that's not available? What happens if you can't reliably track objects? And so can we even generalize this a step further and still define the safety net if we say we don't have access to object tracking? And so this is an example where we thought this might be useful. And this is an autonomous wheelchair navigating in cluttered hallways. I can tell you I am very excited to be back in hallways and campuses that look like this, to be around rich human environments once this whole pandemic is over. But what we're looking at here is if you can imagine, in these cluttered hallways and these cluttered pedestrian ways, it might be hard for a system to identify and track every single one of those humans moving throughout the space. And further, maybe that's just a lot of computational overhead that you'd rather not spend on this part of your system. And so what we looked at is taking our object-based congestion cost function, and instead of requiring it from each object position and each object velocity, we instead said, okay, well, what if we have just a density? So we can use our LiDAR information and check occupancy at points over time, and then construct a velocity field. So how does that occupancy density change over time? And generalize this object-based cost to an object-less cost that we're calling the dynamic risk density. So this is an approximation of our risk level sets that doesn't rely on explicit object tracking, and still gives us the ability to tune our allowable risk. So to take slices of that cost function to set our allowable versus restricted planning spaces. And what we think is really powerful about this abstraction in terms of a safety net is that it's agnostic to your obstacle type. So to the system, it's really only checking occupancy. So tables and columns are treated the same as groups of pedestrians, but further, we can handle the very strange objects that you might see, such as strollers and suitcases and garbage bins, And all of these objects that are very normal for humans to have are things that might trip up your pedestrian detection or your pedestrian tracking algorithm. And so in this way, we can create just again, a safety net that runs below your planning stack and can look at how to kind of make a little bit more smooth navigation through this. So here we're looking at the robot trying to drive through the hallway. It comes across the crowds. We have students stepping in front of the wheelchair. And ultimately, while it's not the smoothest operation, maybe an expert human could drive a little bit better, we're still able to move through these congested and tight spaces without getting completely stuck, because we're taking into account this velocity information of these different obstacles. And so kind of in the opposite direction of that, we were also thinking, okay, so that was kind of going towards minimal information on safety nets. What if we start to look at adding more information and defining risk of congestion and these kind of allowable decisions with more information? And so this particular, what we are interested in is looking at the unprotected left turn in autonomous driving. So the case where a car needs to cross traffic and join a lane of moving cars, and there's not a signalized intersection. So it's not protected by a light, it's not protected by a stop sign, and instead needs to choose when it is safe to make that decision. And to make it more complicated, this intersection is occluded, so it doesn't have a full view of the system. And so it needs to make some predictions about the risk for choosing to enter the intersection based on what might be behind the occlusions. And so ultimately what we're looking at is what is the risk if an autonomous vehicle chooses to enter an intersection at that point in time? What is the risk that it incurs by entering that intersection? And now we're going to define risk instead of as a continuous safety net, but here risk is the expectation of the number of incidents that will occur. So we took a kind of a summation-based approach to this, which is to say, depending on the types of incidents you expect, we can model this as the sum of all those different types of incidents versus all the different areas that you can encounter. And what we think is agile about this representation is that it allows you to pick and choose what is important in your representation of risk. So you can account for things like traffic density. So based on the flow of traffic, you can say, okay, well, because I've seen this many cars, I expect that, in this much time, this many more cars will appear. You can also model physical occlusion. So the fact that you can't see behind an obstacle, it's what is the risk that there's sort of a car hiding behind that obstacle in that shadow that is just waiting to pop out if you were to move in front. We can also include things like sensor noise. So if we have imperfect estimations of the oncoming traffic, imperfect estimations of their velocities, we can add a component of risk that looks at that noise in the sensor. And finally, we can also add components of risk for other parameters in the system, such as the attention limitations of drivers, which is to say that, let's say that I enter the intersection and you might assume that a car would slow down, but maybe they don't see me. So what is the risk that a car is distracted? Or what is the chance that a car is a distracted driver? And if they're a distracted driver, and wouldn't slow down, what is then the risk of collision based on that distraction? And so what we looked at is we built kind of a little miniature city with some of these dollhouses and the race cars. And we had our cars attempt these left turns. And we did two types of experiments. The first was completely autonomous, where the car used the locations of these other vehicles that it could see and would assess the risk and choose to go out and make the turn when there was not an excess of risk. The other type of experiment we looked at was what we called a guardian controller. So here we had a human driver attempting to make this turn, and the viewpoint of the human driver was 3 webcams shown on the lower section of the screen. And the guardian system was running this risk calculation on top of the actions that the human was taking, and would intervene if the human was taking an excessive amount of risk. And it would intervene in a couple ways. The first is it might not allow the human to enter the intersection. So if the risk was too high, it would say, no, you can't go forward. The second was if the human starts to enter the intersection, but then new information presents itself that there's an increase in risk that was unanticipated, it might also augment the velocity of the human driver as they're making that turn, such that they either speed up to finish making the turn or slow down based on the cars that are coming. And so overall, I think these are just a few ways that we can think about risk in the system, and ways that we can think about handling clutter and cooperation, either through creating these risk abstractions or through creating different safety nets of the system. At this point, I'll switch over to kind of the next topic, which is looking at what does it mean for autonomous vehicles to have social behavior. So again, we're looking at this unproductive left turn, and we've got an autonomous vehicle that needs to make this turn, and there's oncoming traffic, and that driver is human. So if these were both autonomous vehicles, it would almost be easier, because you could imagine the autonomous vehicles would communicate with one another and negotiate that intersection. However, with humans, we notice that there's kind of this multiple decisions that they could make. And how do you know, or how do you predict when the human driver is going to maybe be a nice human driver and slow down ever so slightly, such that that's your cue to go ahead and take that left turn? Something that we can recognize on the road, but is hard to really intuit as an autonomous vehicle. On the other hand, what if they're a little bit more selfish of a driver, and they see you want to turn and they actually speed up, so that way you have to wait to make that turn? And this, in general, is an example of a social dilemma. So a social dilemma is a type of game. In this case, we're thinking of this as a game, where the odds of the individual are not in alignment with the odds of the group. So in this case, the objectives of the 2 cars, they're not malicious, but they're not aligned, because both cars want to minimize the time to their destination. But in doing so, they've got these crossing trajectories. So somebody's going to have to make a compromise and give up a little bit of their reward in order for the other car to achieve its goal. And this is a huge problem with self-driving cars. And understanding these kind of intuitive human interactions is causing a lot of difficulty in the implementation and rollout of this autonomous technology on our roadways. It doesn't take many YouTube searches to find examples of these autonomous vehicles failing to merge into the lanes, failing to go at stop signs. And so anecdotally, you can see the examples of human drivers taking advantage of the overly conservative autonomous vehicles. But more seriously, we also see that self-driving cars, when involved with crashes, are involved in rear-end collisions. And these are not consistent with the types of collisions that humans are involved with. And so typically a rear-end collision means that the driver behind you didn't anticipate what you were going to do. And sometimes it's a lack of attention, but given the sheer quantity of these rear-end collisions that are happening with autonomous cars, it's more likely that the human drivers are not anticipating the decisions that these autonomous vehicles are making. And so they're not able to react in a way that avoids this collision. And so what we looked at in this is there a better way to not only create a social model for this autonomous interaction, but if we can predict kind of the social component of the human drivers, perhaps we can also design our autonomous control policies to behave in a socially compliant way. So the first step was we looked at tools from social psychology, particularly something called social value orientation, which looks at a behavior model that weighs individual's reward to self versus another agent. We integrate this social model for allowing adaptive personality types into a best response game. So every agent is going to maximize its individual utility as it's solving for its trajectory along the roadway. And we can actually solve for a Nash equilibrium. The key here is that even though every agent is utility maximizing, because of their particular social value orientation, or SVO, those individual maximums are going to be different depending on the different personality types. And we also learned our reward functions, or tuned this utility function based on the NGSIM data set with highway driving in California. And so returning to this example of the social dilemma, we propose that the social value orientation is what can differentiate these two cases. That if we can identify an SVO preference of a human driver, then we can better predict whether or not they're going to yield and allow us to make the turn first, or if they're instead going to continue forward and we need to wait for them to make that turn. And so what is the SVO? I know this is not something that maybe we see every day. And it's a classic kind of metric from social psychology, and the classic experiment within social psychology to measure SVO is asking participants to split $100 with a stranger. So here the reward is money. So here we've got this $100 reward, and participants come into the room and they say, here's $100. There's a stranger in another room, decide how to split it up. And maybe this person decides that they don't need the money, so they're going to keep none of it and give all of it to the stranger. This corresponds to an altruistic decision where the reward to themselves is 0 and they've maximized the reward to the other agent. And we can represent SVO as an angular orientation sort of between these axes of reward to self versus reward to other. So that altruistic decision where they've maximized the reward to the other is equal to an angle of pi/2. The next thing might be kind of a 50-50 split. So you decide, okay, I don't know this person, but it seems fair to keep $50 and give them $50. That's what's known as a pro-social decision. The reward to self and the reward to other have been equally weighted and sort of are jointly prioritized. And finally, you could say, I don't know this person, they're a stranger, why would I give them money? And you decide to keep all $100 and not give them anything. And that's what's known as an egoistic decision, where you've maximized the entire reward to self, you've kept the entire $100, and given no reward to the other agent. So returning to autonomous driving, we can find ways to define these reward to self versus reward to others, where here the reward functions are really based on driving. So it's based on your efforts in driving, braking, and acceleration, things like how many departures do you need to make from your trajectory, the time to your destination. And you can create a complicated reward function, but fundamentally still say, if I can predict the other agent's reward versus my reward, then I can weight these different SVOs based on how they seem to prioritize it. And what we actually found is that if you look at the full circle of SVO, that we also found that there were some competitive categories of driving. And competitive means that not only do you maximize your reward to self, but you have a little bit of a minimization of the reward to the other agent. And so in that analogy of splitting $100, a competitive outcome would be not only do you keep $100, but you also steal $5 from the stranger. And so with this SVO, if we can predict the human driver's SVO, then we can say, okay, an altruistic agent is going to be the type of agent that slows down and allows us to make the turn, whereas an egoistic agent is going to be the agent that doesn't care that we need to make the turn, instead is going to continue prioritizing their trajectory, and we'll need to wait and make the turn after they go. Now, to validate this, we looked at the NGSIM data set, and we looked at our trajectory predictions of entirely just human drivers. And we looked at kind of a traditional utility maximizing policy where you just assume that all agents are maximizing some static utility function and every agent is the same, versus adding in our component of SVO. And what we found is just by adding the single parameter into our system, we could actually improve trajectory predictions by 25% over a baseline estimate. And in this video, we show how SVO is not a static intrinsic property, but is actually dynamic and can change throughout the course of an interaction. And so here we see a purple car that needs to merge into a lane of traffic with a green car. And so as it needs to move in and as that merge lane runs out, we see that it becomes more competitive as it really needs to get over, because otherwise it's going to either need to stop suddenly or needs to avoid the collision. Conversely, that green car, as it gets closer and as that first car needs to come in, we see it becomes a little bit more pro-social and drops back to increase this gap that allows that first car to move in. And then once that gap is open and once that car is merged, it'll actually become more egoistic again and move forward and close that gap and perhaps prevent other cars from joining in. And so overall, we were able to look at the entire data set, and we found not only just that we can predict SVO dynamically from these vehicles, and we're predicting it based on a 2-second clip of their trajectory. So looking at the trajectory from their last 2 seconds and what SVO best matches that trajectory. So it's not a lot of information and it's not a lot of behavioral prediction that we're doing. And we can find different trends in how SVO corresponds with different behaviors. So for example, if we look at those merging vehicles, that consistently a merging vehicle is more competitive than a non-merging vehicle. And this makes sense as humans, is that when you need to make that merge, you do need to be more selfish. You do need to take actions that you ensure that you get into that lane of traffic. But this is a way that we can translate these sort of human intuition points into information for autonomous vehicles. And then we can use this to create some simulations of autonomous vehicles in common traffic scenarios. But so to design this kind of autonomous policy, we're going to design this utility maximizing policy. And what a utility maximizing policy, if you're programming or optimal control, every agent might have some individual reward function, and their reward depends on how they move and the control actions they take over time. And at every point in time, they can choose a different control policy, which is going to correspond with different reward functions. And over some time horizon, we can sum those individual rewards into a utility function. So we can look at all of these different possible choices and then find the single control policy that leads to that maximum utility or that maximum accumulation of rewards over time. To create this joint reward with SVO, instead of having an individual reward policy, our agents are going to use the SVO parameter to create a weighted function between their individual reward, their reward to self, and the reward to the other agent. And so what this ultimately looks like is that we can still construct these utilities over the time horizon and still find a maximizing policy, except those policies are going to inherently have this preferential weighting of the SVO agent. And so if you have an egoistic agent, that really reduces to the same as an individualistic policy where they put no weight on the reward of the other agent or no weight on the actions of the other agent. Whereas conversely, an altruistic agent is going to only care about the other agent. So if they see a conflict in their trajectories, they may entirely replan their path because that gives the other agent its maximum reward. And so in some simple simulations, we can show that if we can identify the altruistic driver that slows down just enough to create a gap for us to turn, that autonomous vehicle can recognize that signal and recognize that cue and know that it's safer to make that unprotected left turn, whereas it would need to wait for the other egoistic drivers. Similarly with merge lanes, if they're all around egoistic drivers, it'll have to wait for those cars to kind of pass before it can merge from the lane that's ending into the other lane of traffic. But if we have pro-social drivers, those pro-social drivers will actually create a gap for that autonomous vehicle to merge. And while it may be kind of hard to see over Zoom, it turns out that the pink car and the green car space themselves out just slightly that allows this autonomous vehicle to merge in. So we think this is a really interesting first step in creating more socially compliant systems and thinking about ways that we can bring behavior models into the different systems. And it's not just limited to autonomous driving. We can also think about these social distributions and think about how we can encode this geometrically to do a lot of distributed navigation. So if we can encode their kind of SVO preference in a geometric sense, we can give selfish agents larger cells as they're planning paths through the environment, and that larger cell is going to give them sort of priority over navigation to different points. And we can take some more traditional multi-robot navigation through Voronoi-based navigation and look at how we can even encode these social parameters into this just geometric notion of larger versus smaller cells. And so just to kind of spend the last few minutes of the talk, I wanted to spend a few minutes talking about some ideas of what it means in socially aware robot design. So I've spoken a lot about different tools to maybe design cooperation or design socially aware systems where it thinks about the behaviors of others, but how do we actually look at a robot design and think about ways in which we can design for human environments and also be aware of the certain design parameters of the robot when we're making those decisions. And so the motivating case here was last spring when the COVID pandemic sort of shut down everything and really changed, as I'm sure, many directions of research. We were approached by the Greater Boston Food Bank at MIT to see if there was, robotic solutions for different types of disinfection. And the idea here was that, workers are being exposed to, COVID-19, and this is a food bank, an essential operation that cannot shut down. And so how do we, is there a robotic solution that can make a safer environment for the humans without, increasing, if we think about disinfection, having humans do a lot of the disinfection might be putting those folks at risk. And so, we looked at creating this UVC robot because we know that UVC disinfection is effective at neutralizing different viruses and bacteria and pathogens, and seeing if we could create something that can improve the safety of the human workers, while still being aware of the risk the robot presents to the humans. So part of the reason the robot presents a risk is because UVC light is not safe for long-term human exposure. So the same way that it disinfects because it causes damage to microorganisms and prevents the RNA and DNA from replicating, is the same mechanism, which is that if humans are exposed to this, it can cause both eye damage over long exposure times, as well as sort of a supercharged sunburn and skin damage. And so while this is a promising technology for different types of disinfection, it also needs to be carefully handled. And it's not something that humans can go around and maybe like wave UVC wands in an environment. It's also really interesting for robotic applications because the ability or the efficacy of UVC disinfection depends both on the distance from the lamp source, so the distance of that UVC light, as well as the total time of exposure. So if we think about a mobile robot versus a static fixture, a mobile robot can move to where it needs to go and disinfect versus just stay in one place. To get into a little bit more details, when we talk about disinfection, it's typically talked about in terms of the number of log reductions of whatever pathogen or microbe we're trying to eliminate. And so this is the remaining population over the initial population. So a 1 log reduction would mean that 90% of the initial population has been neutralized. 2 log is 99%, 3 log is 99.9%. And this is log linear with respect to time across pretty much any type of pathogen. And so what's an important takeaway is that if you want to disinfect to some 99.9% threshold, it's going to take 3 times the time as disinfecting to 90%. So again, emphasizing that these mobile solutions where you can actually drive up and change the dosage over time makes it much more desirable for efficiency purposes than just static fixtures. And while we saw kind of a rise in curiosity in this technology during the COVID pandemic, it's been around for a long time and is effective against many different types of things. So you can think of things like mold spores, tetanus, tuberculosis, and the range, the target range we were looking at specifically for COVID disinfection is in the same range that can neutralize other types of foodborne pathogens such as Salmonella, E. coli, and Listeria, as well as other human viruses such as MRSA and influenza. And again, this is a technology that's existed in things like water purification, hospital room disinfection, as well as HVAC and kind of industrial food settings. And so part of what motivated this project in particular is that at the Greater Boston Food Bank, there were up to 50 pickups by the partners and distributions per day. So, up to 50 different groups of people coming through this warehouse to pick up food that would later be distributed to the local communities. And so while it's a very busy space, it also means that there were a lot of perhaps chances where if you had an infected individual, you could also see community spread just by the number of different people passing through the shared space. And so what we looked at was a robot that would kind of patrol the shipping floor between shifts of workers. So it would patrol at night. And ultimately what we were looking at is trying to mitigate the spread between those shifts of workers. So from one day to the next, can we provide some additional disinfection before the next shift of workers comes in? And in this case, this was overnight, but you could imagine that if you had kind of breaks in shifts, you could also deploy more frequently. And really why this is important and why we should consider these types of alternative solutions is that, with things like COVID, we saw a dramatic increase in food insecurity. And so a place like a food bank, which is an essential business, really couldn't afford to shut down, because food banks are one of the first lines of defense against food insecurity. And so simply shutting down the warehouse because of its large number of distributions or preventing these distributions from happening really is more damaging to the community than, it's really weighing that risk of transmission versus the risk of or the cost to the community at large. And so this is just a video of our robot kind of driving around. So we, looked at different kind of path planning algorithms. I think the video froze. And so it would, kind of patrol the different aisles at night and kind of provide the disinfection capabilities. And because this is a robotic system, this also allows us to map out the amount of dosage that we applied through the environment and kind of keep track of where dosage was, and perhaps, in kind of future work, look at adaptive dosage control. So if you want to meet a minimum spec, you can have the robot drive around and meet that. And so those are just a few ways that we've thought about both cooperation and social behaviors for our different robotic systems. I'll go ahead and wrap up here and quickly thank the many wonderful co-authors that I've worked with on all of these different projects, as well as the different funding sources.
Thank you, Alyssa, for that beautiful talk. I see some familiar faces here. So questions are lining up in the chat, and we'll get to a couple of them in just a second. I wanted to ask you, just to follow up on the socially aware robot, was there some planning or sensing in that robot that was specifically tuned to watching for and avoiding humans?
For like the wheelchair?
For the food bank.
Or for the food bank. Yeah, so that is, so in this case, we started the deployment running when the building was alarmed. And so we had sort of an external alarm system telling us that there weren't humans. But yes, it's absolutely critical going forward, using motion detection. So the robot is equipped with LiDARs, it's equipped with depth cameras, RGB cameras, to also add that kind of human sensing and reliability.
Very, very good. Very cool application. And then secondly, on Dr. Leonard's favorite example of the left-hand turn that he faces every day going into work, did your experiments with using the Guardian system on the toy robots produce an algorithm that was successfully deployed, or you think will be successfully deployed in future autonomous vehicles?
Yeah, so this is one of those things that we actually were able to pass off to Toyota Research, and Steve McGill and Guy Rossman were sort of leading that team there. And I know they took that project and then deployed it on some of the prototypes out at Michigan. So unfortunately, I wasn't able to join those experiments, but I do see it. I've heard positive updates that it's continuing to work its way kind of into the prototype cars and refine its capabilities.
Thank you. Then I noticed in the chat that social value orientation elicited a lot of response, particularly the question about whether it is whether there's a different orientation prevalent in one part of the country or of the world than another part, and do you want to train your agents differently based on that? That would be one, I think, general theme through here.
Yeah, I think that's a fascinating question, and I'd like to say, anecdotally from my experience, I find that Boston drivers are more entitled than maybe perhaps New York drivers are a little bit more aggressive to the LA drivers, which are just whimsically reckless. So I do think it's important to use local data and have a system that can adjust and adapt to those local conventions as well. And I think beyond just our social parameters, as we think about encoding rules for these cars, knowing what are sort of the local ways or local kind of informal rules that people use is also.
Or maybe learning those rules in a safe environment in the local area before going on to the Beltway, for example. So a question from Dr. Taylor. The formula for combining utilities seems wrong. Why use sine and cosine for the weightings?
Yeah, great question. So sine and cosine, so we take this angular notation for the parameter, and so sine and cosine between 0 and pi over 2 gives us a kind of 0 to 1 weighted mapping. Other representations of SVO are more of a linear parameter between 0 and 1. So you could also take a weighted average that way. So ultimately, this formulation was just to create a weighted average between the the self versus other.
But at pi over 2, even if both utilities are identical, you get a higher utility.
Okay, I see what you're saying about the
or pi over 4 rather. You know, 45 degrees.
Yeah, and so, but I think that's okay in this context, because if they both want to maximize the joint reward, it's okay to say that jointly at that point where it is kind of the optimum, that you do end up with a higher joint reward.
Yeah.
It's not necessarily a zero-sum game.
It's ultra, you know, it's arbitrary anyhow. It's a heuristic, so.
I think I'll turn it over to the audience at this point. I think I've tried to address the chat questions about the SVO regionality question. If there's other people that'd like to jump in, please unmute and ask your question.
Yeah, this is David. How are you doing? It was a great presentation. I really enjoyed it. So I have a question about some of the work that you're doing on versus sort of the fact that you have altruism versus egoism or somewhere in between, right? So and you were using that methodology to perhaps explain or inform maybe algorithms how they might perform differently. And you mentioned that rear-ending accidents happen, frequently with unmanned vehicles. So the question is that could it be that maybe it's not about, in those cases, altruism versus egoism, but just that the way that unmanned vehicles behave is different than what I would expect a person to do in the same situation, as opposed to
Yeah, absolutely. So I think SVO is a promising metric, but I don't think it's the only metric. And so I think trying to design, it's almost like, to really integrate the autonomous vehicles, almost need to pass a Turing driver's test of being able to be indistinguishable from a good human driver. And I think in the case of rear ending, I think some of that also is maybe a hyper conservative approach as it's going towards the intersection. So it's braking sooner and more aggressively to avoid the risk of, overshooting the intersection or approaching that. Whereas, if you've, I'll just say this kind of regionally in California, you have what's known as the California stop, which is you don't really actually stop at a stop sign, you just sort of roll on through. And so if you have a vehicle that's programmed to do a legal stop versus the California stop, and that also is going to lead to a mismatch in understanding. Not that I advocate for autonomous vehicles to necessarily break the laws or break the rules of the road, but it is important to understand these sort of nuances.
Yeah, I understand that some of these accidents happen because exactly the autonomous vehicles do obey the laws, whereas people don't expect everybody to obey the laws. So there's confusion and mismatch.
We've got time for one more. Last questions? Okay, very good. We want to thank our speaker, Alyssa Pierson, for this wonderful talk, and thank everyone for attending. Please join us next month on the 20th of April, where we will hear from Larry Peterson of Princeton. Thanks, everyone, and have a wonderful day.
Thank you all. Thanks again, Alyssa.